Hi everyone. Today we'll talk about the direct substitution property. First, let's talk about where the direct substitution property comes from. Let's find the following limit using the limit laws. If you would like to try this exercise on your own first, you can download these notes using the link in the video description. First, I apply the sum law and I rewrite this limit as the limit as x goes to 1 of x squared plus the limit of 5x as x goes to 1. So I split this limit into two limits. I continue. I note that x squared is the same thing as x times x, so I can rewrite this as a limit of x times the limit of x by using the product law. I can also rewrite the limit of 5x as 5 times the limit of x by the constant multiple law. I can take this 5 and move it outside of the limit. So I can rewrite this as the limit as x goes to 1 of x times the limit of x as x goes to 1 plus 5 times the limit of x as x goes to 1. In the first line of this computation, I use the sum law. In the second line of the computation, I use the product law, and I also used the constant multiple law. And if you don't know what these laws are, I recorded a video about the limit laws. I will add a link in the video description. Now, the remaining limits are basic limits. The limit of x as x goes to 1 is 1. So I have 1 times 1 plus 5 times the limit of x as x goes to 1 is again 1. So altogether, I get 1 plus 5, which gives me 6. So this limit is 6. What I want to point out is that if you had plugged in 1 to this expression, you would have obtained 1 times 1 plus 5 times 1. So people realized that thanks to limit laws, instead of writing all that work here, you can simply take 1 and plug it into the expression and obtain the same result. That property is called the direct substitution property of this function. That direct substitution property holds in general for polynomials and for rational functions. For example, if you have a function that is a polynomial and you want to compute the limit of that function, as x goes to any number, let's say as x goes to a, all you have to do to compute this limit is to plug in a to the function. Similarly, if you have two polynomials and one is divided by the other, you have f of x divided by g of x, and you want to compute the limit of this function as x goes to some number a, then what you can do is simply plug in a to the numerator and to the denominator. So to compute f of a and divide it by g of a. You can use that rule only if g of a is not 0. If g of a is 0, then you would be dividing by 0 and you're not allowed to use the direct substitution property. But if g of a is not 0, then you can use this property for any polynomial divided by a polynomial. Let's see if we can apply this property to a few examples. In the problem below, I'm asking you to compute the limits using the direct substitution property. If you would like to try this on your own first, don't forget to stop the video now and attempt it on your own. Now, in the first example, I have a polynomial, x squared plus x plus 1. I'm supposed to compute the limit as x approaches 2. What I could do is I could use the limit laws. I could rewrite this as the limit of the first term, the second term, and the third term. Then on the first term, I could use the product law, and then I could use basic limits to compute this limit. Or I can use the direct substitution property, which means I can simply plug in 2 to this expression. When I do that, I will get 2 squared plus 2 plus 1. That gives me 4 plus 2 plus 1, that is 7. So the limit of this polynomial as x approaches 2 is 7. In example B, I have a rational function, a polynomial divided by a polynomial. Instead of using the quotient law and then other limit laws to compute this limit, I will apply the direct substitution property, which means I will plug in 3 to the numerator and to the denominator, and I will get 3 squared minus 3 plus 6. In the denominator, I will get 3 plus 1. So in the numerator, I have 9 minus 3 plus 6 divided by 4. 9 minus 3 is 6, 6 plus 6 is 12, so that is 12 divided by 4, which is 3. So this limit is 3. Thanks to limit laws, we have the direct substitution property, which simplifies and shortens all the calculations. Let's try one more problem. Now I give you two functions, and I want you to find their limits as x approaches, in the first case, 1 from the left, in the second case, x goes to 2. In the first example, I have the limit of this expression as x approaches 1 from the left. If I had x approaching 1, not from the left, not from the right, but x just approaching 1, I could use the direct substitution property. Thankfully, the direct substitution property also works for one-sided limits. So that means I can simply plug in 1 to this expression to compute this limit. And I will get 1 plus 1 squared plus 1 to the 3rd power plus ... plus 1 to the 98th power plus 1 to the 99th power plus 1 to the 100th power. 1 to any power is 1. So each of those terms is 1. So I get 1 plus 1 plus 1 plus ... plus 1 plus 1 plus 1. I believe I have 100 terms here. Adding 100 terms, each one of them being 1, gives you 100. So the limit of this function as x approaches 1 from the left is 100. Let's try to do this in example B. I have a rational function, polynomial divided by a polynomial. I plug in 2 and see what I get. And I get 2 squared minus 4 divided by 2 minus 2. In the numerator, I get 4 minus 4, that gives me 0. In the denominator, 2 minus 2 gives me 0. I obtained 0 in the denominator. According to the direct substitution property, I'm not allowed to use the direct substitution property whenever the denominator is 0. I can only use it when the denominator is not 0, which means I was not allowed to use the direct substitution property here. So, how otherwise can I compute this limit? Well, we will answer that question in one of the next videos.